Hello, welcome to EEE 117. Here we're going to talk about a continuation of three-phase power. So just to remember, last time we talked about the basics of a balanced three-phase system. All right. So here's kind of just let's zoom out a little bit, a review of what we covered on the last period. So here we have a three-phase system. This is a Y-connected source with a Y-connected load. You have three major voltage sources. These three voltage sources are VA, VB, VC, where you have the same the voltage magnitudes, and they're 120 degrees apart. That's the definition of a balanced system. You have three currents typically on the system, I, IB, and IC. So you have three magnitudes all equal. You get a phase shift 0 degrees, a phase shift plus 0 degrees, the same phase shift minus 120 degrees, the same phase shift plus 120 degrees. You typically have a phase shift on the current because there might be an inductor or capacitor in the system, so it's going to change the phase shift from the voltage. You do have a neutral current as well. I didn't write it here because it's pretty much 0 amps in a balanced system, right? How do we relate each of the different phases, assuming a balanced systems? Again, the magnitudes are always equal per phase, and then 120 degree separation between each phases. Okay, so just know, as long as you know VA and IA, you know the whole rest of the power system. Okay, now we're gonna have to go a little more deeper because there's more voltages than just what we mentioned before. So typically voltage, if you remember from Engineering 17, is always the difference from point A to point B. You can't have a voltage with only one node. You need to have a reference. All right. So all voltages always have something on the positive, subtract by something on typically the ground or some other part of the circuit. Now in the power system, because we have three different voltage sources, it's a little bit harder just to stick a ground everywhere and say everything's zero. So we got to be a little mindful of our voltages. So a lot of times in the three-phase power systems, we use a two variable naming convention, where you could have a voltage called VAN, where the subscript A here stands for A phase, and the subscript N stands for the neutral voltage. Mathematically, VAN is going to be the A phase voltage minus the neutral voltage. So it's always a difference. Remember, voltage is always some point minus another point. Now, usually the neutral voltage is 0, so we could drop the N, but if I want to be technically accurate, we should be writing VAN and VBN and VCN, which means VB minus VN, VC minus VN. Okay, so you should get pretty comfortable with this two variable naming convention, VAN, VBN, VCN, if you really want to be accurate to our naming convention. We also have currents IA, IB, IC. We don't need a double naming convention here because current does not require subtraction. Current is you're not taking one part of the current and comparing it to another. Current is just what flows in the wire, and that's it. Okay, so voltage is always a difference. So there's always 2 points to compare. Two naming conventions. Current, there's no comparison. It's just whatever's on the line. So it's a single variable. Okay. Now, with that being said, we could start talking about the Y-connected load from last time. We have IA, IB, and IC coming in to A, B, and C. But notice A phase, this is a voltage on A phase right here to this positive terminal of the load. On the negative terminal load right here, we have the neutral voltage. So VAN is actually the A phase voltage minus the neutral voltage. That's the voltage across ZA impedance. Okay? So we've been using this, we just never formally called it a voltage. It's VAN, VA minus VN. All right. We have another voltage here from B phase. And notice B phase touches the positive terminal of the impedance, and the negative terminal impedance goes to neutral. So the voltage across this resistor or impedance and the Y-connected load is VBN. Again, that two naming convention where VBN is VB minus VN. The third one is C phase, where if you look at the line voltage, goes all the way to the positive terminal of the impedance, and the negative terminal impedance is the neutral. So this is called a VCN voltage, which is VC minus VN. So these are three voltages you'll see in a Y-connected system. Okay. And this is typically called a line to neutral or a phase. Typically, line to neutral is the main thing you call it because you have a line voltage and you take a difference of the neutral voltage. So line to neutral voltages. I think we'll cover that later. The next type is we have delta connected loads. And notice the voltages here are different, mainly because there's no neutral. So we can't say VAN in a delta connected load. So if you look at Z delta here, the positive terminal is on the A phase voltage, and the negative terminal is on the B phase voltage. So the voltage across Z delta is actually A minus B. So here we could say VAB is VA minus VB, which is a voltage across a delta load right here. We could do the same thing for the next delta load. The positive terminal is on the B phase up here, and the negative terminal is on the C phase down here. So this is another voltage between here and here called VBC, which is VB minus VC, the voltage across this impedance on the delta. Lastly, and if you notice, it's always positive and negative, then positive and negative, just to keep the convention going. The last Z delta is going to have a positive voltage on the C phase, and then a negative voltage back on the A phase. And the voltage across the Z delta is VCA, which is C minus A. So you could kind of see a little like cascading pattern where you have VB. So VAB has B in the second term part, but then VBC, that for VBC voltage, VB goes back to the front. So it's kind of like a little diagonal this way. And VC kind of diagonals over as well, and VA diagonals back to the top. Okay, so the way I like to think about these voltages is we call them line voltage, to kind of like move over diagonally one slot. Okay, that way it's kind of symmetrical. Okay, no, where's the neutral here? Remember, deltas don't have neutral, so we can't even say AN, BN, CN. The only choice we have is VAB, VBC, and VCA. And these voltages are very typical, which you'll see. Okay, some people argue, well, why can't we use VBA and then CB and AC? You can, but it's very unconventional. We typically go alphabetically A, then B, B, then C, then C, back to A. There is no D here, so we want to say C, D. Okay. So that's for your delta connected loads. So you have a different type of voltage to compare. Now, when we put them all together in the power system, you're going to have different type of voltages. Now, for a Y-connected load, the phase voltage is a phase voltage is technically the voltage across the impedance. So this phase voltage is VAN, VBN, and VCN because that's the voltage across the impedance, right? This is called phase voltage, ABC to N for this Y system, Y-connected load, right? Another way to call this is a line to neutral voltage as well. So phase and neutral voltages and line to neutral voltages, they're kind of mixed back and forth. I think if you want to be technical, it's probably the line to neutral is a more formal definition, but I've heard phase and neutral pretty common as well. Okay. The big difference here is just notice the neutral right here. That's the big takeaway. Okay. We have we call line volt. So the previous one, we call it phase voltages. So typically phase voltages are on the actual Y-connected load. So phase and neutral. That's what I would use, phase and neutral. That's my most common go-to. You have line voltages. So line voltages, I call it a voltage on the power system itself. Now notice when we have the transmission system in the air, towers everywhere, we don't have a neutral on the high voltage system at all. So we can't say VAN, VBN, and VCN on the transmission system because there is literally no neutral. So our only option is to always say voltage between the three wires. You have VAB, VBC, and VCA. These are called line voltages because this is a voltage on the power lines. Okay. So the second set of voltages are VAB, VBC, VCA. They're measured between always two live voltages. Okay. We call this line and line voltages. Rarely you might hear phase-to-phase voltages, but this is kind of incorrect. Okay, phase-to-phase voltages don't really make much sense because phase voltage, when you say phase voltage, you're typically looking at the load side, right? But we're mainly talking about voltages in the power system. I would opt to use line-to-line voltages if I were you. But if somebody says phase-to-phase voltage, there's like a very high chance they probably meant line-to-line voltages. Okay. So what that means is there's technically 6 voltages. VAN, BN, CN, and then VAB, BC, and CA. So there's now 6 voltages to keep track of. Now the question is how do we calculate these voltages? We have definitions, but let's put some math behind it. So the phase voltages on the Y load, this voltage between ZA is A phase minus the neutral phase. So VAN minus VN, well, let's figure it out. I'll say VA is 2.4 angle 0 degrees kV. So if I say VAN is 2.4 angle 0 degrees minus VN, the neutral voltage, which happens to be 0 because they're balanced, it's the same number. So a lot of times just the voltage for VA is the same as VAN, unless your neutral is different. VBN is the same thing except negative 120 degrees. VCN is the same thing except positive 120 degrees. That's a 120 degree separations. Magnitudes are all the same. Okay, so line to neutral is very straightforward. It's typically just a voltage on the line minus 0 because the neutral is 0. Now, if the neutral is non-zero, because you have one of these is offline, then this number will be a little bit different. You'd actually have to do the subtraction. But typically in this course, because it's introductory, we're not going to talk about that. Okay. Now, what about the line voltage? How do we calculate VAB? Well, mathematically, we could literally say VAB is VA minus VB. We know VA is 2.4 angle 0 degrees kV, but we got to subtract VB. We know VB, that's 120 degrees apart with the same magnitude. So we're going to subtract 2.4 kV angle negative 120 degrees. Now, going to calculate on number crunches, you're going to get 4.16 angle positive 30 degrees kV. Okay, it's kind of a strange number, but I guarantee if you mathematically do this is the number you're going to get. Now, one thing to note is look at the line voltage. VAB is higher than the just individual voltages. And there's a little degree phase shift. So there's something up here. We're going to have to check that out. Okay. Now, let's talk about BC phase. So we saw VAB. VBC is the blue one right here. It's from B phase positive to C phase negative. So VB minus VC. VB is 2.4 angle 120 degrees kV minus VC, which is 2.4 angle positive 120. I should write kV right there. Do the same number crunch, you can get 4.16 angle negative 90 degrees kV. So you notice you got, wait, this is negative 90 degrees. The previous one was positive 30 degrees. That's 120 degree phase shift. And then 4.16 still carried over. So the same properties will work for VAB, BC, and CA. As long as you know VAB, the other two are going to be the same magnitude. Look at CA, 4.16. What's the phase shift? It's 240 degrees off, right? Or if we compare to A phase is positive 30 degrees. You can add 120 to get positive 150, okay? So VAB, VC, VBC, VCA are the same properties of balanced systems. 120 degrees apart, same magnitudes, okay? And note, remember, this is the voltage between the two phases, it has nothing to do with the neutral. Even if the neutral is drawn here, we're not talking about neutral here, though that's these three. We're talking about the voltages on the power system, okay? Now let's draw some vectors to represent the difference. You have VAN, which is 2.4 kV angle 0 degrees, VBN, which is 2.4 angle negative 120 degrees. That's why it's down to the left. And VCN is up and to the left because this is 2.4 angle positive 120 degrees. Okay. Now, the VAB, which is we just calculated, notice that it's longer because this is 4.16. And we're positive 30 degrees. So we're up and to the right a little bit here. And notice, although the two vectors, they're shifted counterclockwise by 30 degrees, and they're longer. So if I actually erase the red vectors and just look at the blue ones, which is our line-to-line voltages, they're going to be 120 degrees apart, and they're going to be the same magnitudes. If I draw a circle, they'll all touch because they're the same magnitude. Okay. So these are all 6 voltages you'll see in a power system. Phase and neutral, VAN, VBN, VCN. Line-to-line voltages, VAB, VBC, VCA. 6 voltages you got to keep track of. Okay. Now, again, remember, as long as you know VAN and VAB, the other two are very easy to calculate. They're 120 degrees off. Okay. Now, one big question is, if I know VAB, can I find VAN and vice versa? Right? Mathematically, we showed you how to do it. There's some vector subtraction involved, but we don't have to get the calculator every time to do that. There's a pattern we realize. If I know VAN, so I know the voltage from A phase to neutral on this Y-connected load, I can calculate that, or I can measure it. I immediately know VAB because if you look at the math above, previous page, the only difference between these two is the VAB is square root 3 bigger than VAN, and you're always adding a 30-degree phase shift. So if you go back and you number crunch this, 4.16 is square root 3 times higher than 2.14, and look at the phase shift, it's only a 30-degree difference. Okay. So that's the rule for going between line voltages and the phase voltages. So if you ever have VAN and you want to find VAB, square root 3 more, add 30 degrees, you're done. If you have the line-to-line voltages, VAB, and you want to go to the line phase to neutral voltages, VAN, divide by square root 3 and subtract 30 degrees, go backwards. Okay. Vectorially, what's happening is, remember, VAB is VA, which is this red vector on the x-axis. You got to subtract VBN. We know VBN is 120 degrees off, but how do you vectorially subtract things? When you subtract, you got to take this vector and slide it onto the first vector and have the arrows point at each other. That's how you mathematically add vectors together. So, I mean, subtract vectors together. So you take VBN, slide it over, and then make sure the arrows touch, and then you could draw VAB, which is right here. And then this will guarantee to be a 30-degree phase shift. Because technically this is a 1 square root 3 isosceles triangle, because this is 30 degrees down here, this is another 30 degrees, and the phase shift between VAN and VBN is 120 degrees. We already knew that. Okay. So this is the big takeaway. Going to line, up 30 degrees, up. Sorry. When we're going two line-to-line voltages, multiply by square root 3. So we're up square root 3, add 30 degrees. We're up 30 degrees. Going from the big line-to-line voltage to the smaller line, the phase and neutral voltage, go down square root 3, divide by square root 3, subtract 30 degrees, take it out. So just remember, line-to-line is always bigger than the phase and neutral. Okay. Okay, so summary of the difference. VAN is always at magnitude, phase angle 0 degrees, that's a reference angle. From here, we could calculate VBN and VCN, we already know that. We could get line voltages, VAB, VBN, VCN, VCA, right? Remember, line voltages are always larger than phase and neutral voltage, so VAB will always be bigger than VAN. Okay. Remember that line-to-line voltages, VAB, always have a positive 30-degree phase shift from the phase and neutral, VAN. Okay. And you just always remember, line-to-line is always square root 3 higher than your phase voltage plus 30 degrees. Your phase voltage is always your line-to-line voltage, divide by square root 3, subtract 30 degrees. And I always draw the small little vector to remind myself, right? X-axis is a smaller phase voltage, that phase and neutral voltage. The longer one is our line-to-line voltage. And it's always above us, positive 30 degrees. So I put this to memory, this little diagram. So anytime I need to convert, I always know line-to-line is positive 30 degrees, and it's also square root 3 longer. 100%. Okay. So that's the summary between line-to-line voltages and phase and neutral voltages. Okay. Now, of course, we got to do some example problems to cement this in. So let's say we have this Y-connected load. I want to find VAB if VAN is 277 volts, angle 0 degrees. Well, remember, VAB is always square root 3 more than VAN, and you add a 30-degree phase shift. So square root 3 times 277 is 480 volts, and 0 degrees plus 30 degrees is a positive 30 degrees. So VAB is always 480, angle positive 30 degrees. 480 volts is a very common voltage you can see in industrial systems, right? So if you ever worked on the, you ever wonder why, you might see 480 slash 277. 277 is your line to neutral version of your 480, which is line to line. Okay. Now we could go backwards. Let's say VAB is 480 positive 30 degrees. Let's back crunch VAN. So VAN is always equal to the VAB, which is line to line, divided by square root 3, subtract 30 degrees. So 480 divided by root 3 is 277, and the positive 30 degree, the negative 30 degrees has a positive 30 degrees added into it, so they cancel out to 0 degrees, which is our original voltage. Over here, we have a diagram. You can see VAN is on the x-axis up to 277 right here. VAB is 30 degrees more, all the way up to 480 point up here. Okay. So that's kind of visually how would you calculate your line to line voltage to your phase and neutral. Okay. Now, let's say we have not A phase. Let's say I give you a different voltage, different phase. So let's do B phase. Let's say VBN is 7.2, angle negative 115 degrees kV. So notice it's not negative 120. So we have like a small phase shift. It can happen. Voltage is not always 0 degrees, and voltage is might not always be perfect 0 degrees, positive 120, negative 120. So VBN is negative 115 degrees. So we're off by 5 degrees, which is fine. Well, let's calculate VBC. So if I know I need to get my line voltage, which is more, so we're going to take square root 3 times VBN, and we're going to add 30 degrees because we're always going for the longer one. Okay, so we got square root 3 times 7.2 kV. We got negative 115 degrees, positive plus 30 degrees, because we're going line to line kV, line to line voltage. That calculation is 12.47, angle negative 85 degrees kV. Okay, so that's our BC phase. Normally, if everything was perfect, this should be negative 90 degrees, but we're 5 degrees off, which is exactly where we were on our line to neutral, right? It should be 120, but it's 115. So this should have been 90, but it's 85. So and that's perfectly fine. So when we draw a vector, notice that VBN is out here. This is between the x-axis, this is negative 115 degrees, and we're out 7.2 kV. And our line to line is a little bit larger at 12.47 kV. And we're positive 30 degrees. I kind of drew, maybe I overdrew it, but I'm trying to show that this is not negative 9 degrees, it's negative 85. So there's a little gap between these two. Okay. Now we could go backwards. Let's say I have VBC, I want to find VBN. So my line voltage divided by square root 3 minus 30 degrees will get my phase and neutral. So 12.47 divided by root 3, and then phase angle is negative 85 degrees minus another 30 degrees. Our answer for VB, this should be VBN, right? So well, I'm going to change that right now. Okay, point. See if I can draw it there. You guys get the idea, right? So just to correct on the fly, this is VBN equals 7.2 angle negative 115 degrees, which is what we have initially up here. Okay. Yep. So just to kind of show you, even if you don't have VA or VAB, you could do it for any other phase as well. Okay. So here's where we're going to take our 15 to 20 minute break. You have a system, a Y-connected system. You have 6 voltages to look at. I will give you the first one. VAN is 277 angle negative 20 degrees volts. I want you to calculate VBN, CN. That should be pretty easy. I want you to calculate VAB, VBC, and VCA. So look through the notes we just did. You should be able to calculate VAB, and VC and CA will just follow suit. Okay. Then on here, I want you to accurately draw all 6 vectors. I already gave you the first one right here. VAN is 277 angle negative 20 degrees. Give me VBN, CN, VAB, VBC, VCA, and try to be a little accurate. Okay. So the big difference is notice VAN is not 0 degrees anymore. We're starting at negative 120, negative 20 degrees. So all your numbers might be off a little bit. Just carry that negative 20 degrees with you the whole time, and you should be okay. So, all right, let's take that break. We'll be back in about 15, 20 minutes, and we'll see how you guys did. So see you in a little bit. All right, hello, welcome back to EEE 117. We're going to continue to check out this exercise about the three-phase voltages, especially the line-to-line voltage and the phase-to-neutral voltages for this Y-connected load. So if you remember, we had a Y-connected load. We have 6 voltages we want to see. The phase-to-neutral ones, VAN, VBN, VCN right here. So VAN is given us 277 angle negative 20 degrees. VB and CN are going to have the same magnitudes, 277 each, but their phase shifts will be off by 120 degrees. So VAN is going to be negative 20 minus 120 degrees, so it's negative 40. VCN is going to be negative 20 plus 120 degrees, net us a positive 100 degrees. VAB will just be the VAN, 277 times square root of 3, because the line is always larger. We're also going to take the initial negative 20 degrees and add a 30 degrees to it. So we're going to net 480 angle positive 10 degrees. VBC will be the exact same, except now, I mean, you could do this math, but at the end of the day, VBC is going to be the same as VAB, except we're going to be angle negative 110 degrees. We took positive 10, subtract 120, we get negative 110. VCA is going to be 480, angle positive 130, because we got 10 plus 120 to positive 130. Additionally, you could go through and do it one by one with the square root 3 and positive third degree phase shift from VB and VCN respectively, but you'll get the same numbers in the end of the day. Okay, my personal opinion, just find VA and VB and CN, just follow suit. Find VAB, VBC, and VCA, just follow suit. It's just easier that way. Now, of course, now we have to sit here and let's try to draw everything out. So initially you had VAN, which is 277 angle negative 20 degrees, right? Remember, VAB should be positive 30 degrees. So it's going to be counterclockwise 30 degrees and larger by square root 3 more. So this is about 480 right here. VBN is going to be over here. Again, shifted over a little bit more than, normally it's negative 120, but we're negative 140. So it's a little bit farther out towards the negative x-axis than normal. Then we got a positive 30 degrees, so it's counterclockwise 30 degrees. We go out a little bit more to 480, so this is square root 3 more than VBN. And then VCN right here, again, is 120 degrees off from VAN. So notice that VN is down negative 20 degrees, so VCN needs to move over extra 20 degrees. So normally VCN is about where VCA is, if we're drawing it accurately, but we're 20 degrees off, so we're closer to this y-axis. So VCN is right here, and then VCA is 30 degrees behind, and this will be a square root 3 more. All right. So here it'll be 480 and positive 30 degrees. So if you look at the shorter arrows, the line of phase and neutral voltages, they should all be 120 degrees apart, equally distant. If you look at a line-to-line voltage, VAB, VBC, VCA, they should all be 120 degrees apart, equally distant as well. Okay, so that's your 6 voltages you'll typically see in the power systems on a vector diagram. Okay, so just to recap, 6 voltages and 3 currents is what we're looking at. Now, the next big thing we need to talk about is calculating 3-phase power. We know how to calculate single-phase power very well, but 3-phase is a little bit different because now we have 3 sources. Remember, we have VB source and VC source. So it's actually not that hard because the system is completely balanced and VB and VC follow suit, IB and IC follow suit of IA. It's as easy as calculating power for each phase and then adding them together. So power for A phase is VAN times IA cosine of theta VA minus theta IA. Very big key here. Notice this is phase to neutral, VAN, not line to line. So you must use your phase to neutral voltage here. Okay? And you have your phase shift of A phase right here. Calculate this, you get power of A phase. Power B phase and C phase, you could calculate individually, but it's going to be the exact same as A and PA. The reasoning why is VAN and VBN and VCN are all equal. IA, IB, and IC are all equal. Even though the phase shifts are 120 degrees apart, when you subtract the difference, the 120 degrees apart will cancel out here. And then your cosine will literally just be like a 20-degree difference for this one. Cosine of theta B minus theta IB will be a 20-degree difference. So this cosine angle will be the same no matter if you're A phase group, B phase group, or C phase group. Okay? Because this all of this is referenced to individual. Are you using VAB, VA, VB, or VC? So because again, three-phase balanced system, it's as simple as three-phase power. It's literally 3 times A phase power. Or we could just say P three phase is equal 3 times VAN times IA cosine theta VA minus cosine of theta VA minus theta IA. Okay, this is a phase shift difference between the voltage and the current. Okay. So this is why A phase is so important. You calculate A phase, B and C phase follow suit. Same thing for power. Okay. So literally three-phase power is just 3 times single phase power. What about reactive power? Same thing. Find Q per phase, add them all together. Q of A phase is VAN. Again, look, make sure you're using phase and neutral voltage times IA times sine theta VA minus theta IA. Okay, this is a power, the reactive power from one impedance of the different phases. So in a Y-connected load, this is the reactance for A phase. B and C phase will follow suit because it's the same impedance, same voltages, same currents. Again, it's a balanced three-phase system. So ultimately, three-phase reactive power is just 3 times A phase reactive power, or 3 times VAN times IA times sine, remember sine, of theta VA minus theta IA. Okay. So as you can see, three-phase power is actually very simple. As long as you know A phase power, as long as you know single-phase power, three-phase power is literally 3 times more. Apparent power, guess what? It's the same thing. Find the power for all 3 phases and add them together. So apparent power for SA is VAN times IA. SB and C is SA. Apparent power for B phase is the same as A phase. Apparent power for C phase is the same as A phase as what? Because again, it's a balanced 3-phase system. And so the S3 phase should be, let me draw it in right now, 3 times VAN times IA, or the 3-phase apparent power is 3 times apparent power of A phase. Okay. So again, just literally everything multiplied by 3, except for power factor. Power factor, you calculate for one phase, the others are exactly the same. So remember, power factor at A phase is cosine angle between voltage and current for A phase, or real power of A phase divided by apparent power of A phase. So we could say P over S. Now, power factor B and C phase, guess what? Are going to be the same as the A phase because PA, PB, and PC are the same. SA, SB, and SC are the same. So why would it change? Okay. So as long as you know the power factor of one phase, all 3 phases are going to be exactly the same. So basically, this is the one time you don't take power factor and multiply by 3, right? You're not adding them. You're just finding power factor of one phase and just assuming everything else is going to be the same. You can even go and say power factor 3 phase is equal to the real power of the 3-phase real power divided by the 3-phase apparent power. You could do that as well. You'll get the exact same number. Okay. So power factor is very simple. It actually stays the same. Now, there is one complication to this, and I'm sorry, but this is a cause of mass confusions in power industry. I hate it to this day, but we have to cover it, and I want to pay special attention. Notice I've been emphasizing every time we do power, any type of calculations, we're using VAN, phase and neutral. Unfortunately, the power system as a whole, the voltages we typically read off of spec sheets and we talk between engineers are line-to-line voltages. They're more common in a power system, right? Because remember, you'll always have line-to-line voltage no matter if you're Y to delta connected loads. Doesn't matter if you're 3 or 4 wire system, you always have line-to-line voltages. Phase and neutral voltages on a Y-connected system only exist when there's a neutral. If there's no neutral, phase and neutral voltages don't exist. So we have to talk about line-line voltage because that's the one that's on always there. It complicates the power calculations because normally we're using phase voltages or phase and neutral voltages, right? Because remember, I initially said apparent power three-phase is 3 times V phase and neutral times IA. We got to replace this with line-to-line voltages because that's what's more common. So remember, if I want my phase to neutral voltage and I have line-to-line voltage, line-to-line is a bigger voltage. So I have to divide by square root of 3. So I'm doing a placeholder. I'm taking VP, which is phase and neutral voltage, and I'm injecting line-to-line voltage equivalent, but I got to dumb it down by square root of 3, so I got to divide by square root of 3. So to calculate the three-phase apparent power with line-to-line voltage, which is what we typically get in the power system, is 3 times voltage line-line divided by square root of 3 times IA. And the biggest confusion here is if you do the math, apparent power three-phase is actually square root of 3 times line-line voltage times IA. And the reason why you have square root of 3 in front is because if you take 3 divided by square root of 3, you can simplify this to a square root of 3 on top. And the reason why this is so confusing is most people, when they see a multiplied by square root of 3, they assume this V line to line is actually VP. Because typically, you don't take VP and divide by square root of 3, right? V phase and neutral is typically multiplied by square root of 3 to get line to line. And line-line voltages are typically divided by square root of 3. So I personally dislike this formula a lot. I like the previous one here. It's more descriptive, just to make sure you understand this middle area is your phase and neutral voltage. But I'm going to be honest, the rest of the world uses this one down here. So just please remember, this square root of 3 is not just converting phase and neutral to line-line voltages. There is a 3 times divided by square root of 3. Okay, I'm telling you, I've talked to 20 years and electrical engineering veterans, and when they bring up this formula, I ask them, well, this is already line to line. Why shouldn't we divide by square root of 3? Bro, their minds explode, right? So I'm harping on this really bad because you will probably get a lot of arguments in your career about the square root of 3. And just be sure you know when to divide by square root of 3 and when to multiply by square root of 3. I swear to God, $20 million projects have been blown out the water because people forget when to multiply and when to divide by square root of 3. So please, 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 please pay attention to this. And at the end of the day, if you're confused, go back to the math, start from a point you know, and then work it out on a sheet of paper to fully understand why you're dividing by square root of 3 and why you're multiplying by square root of 3. Because the engineers would tell you all day long the wrong answers. They believe in circuit analysis, believe in the math, bring out the textbooks to be absolutely sure you know if it's brought into question. Okay? Case in point, this formula right here. Okay, so this is a derivation to it. The textbook answer you'll always see in every IEEE paper and every formula and every spec sheets is S3 phase is equal to square root of 3 times voltage line times IA. So just make sure you're using line voltage for this. Make sure you're using your current here, and you should be good to go. Okay. So as a big summary for your phase voltage and line voltages we talked about earlier, is you got 3 phase voltages, VAN, VBN, VCN. I like to call it phase and neutral voltages to be a little more descriptive. Our line voltages, which I like to call line-to-line voltages, are VAB, VBC, and VCA, 6 voltages. Okay, they're labeled right here as Y-connected load. Remember, in delta-connected load, these phase voltages, VAN, VBN, VCN, do not exist. On the right-hand side is a vector to compare VAN to VAB. Just so you remember, line to line is always larger and it's ahead by 30 degrees. Just go ahead and burn this into your memory. Okay. When we will convert between phase voltages and line voltages, square root 3 times V phase and neutral. So take the phase and neutral voltage, multiply by square root 3, add 30 degrees to get your line-to-line voltage. Okay. If you have your line-to-line voltage and you want to go back to your phase and neutral voltage, VP, take your V line to line, divide by square root 3, and then subtract 30 degrees. So you're going backwards. Okay. And these vectors kind of show a visual representation of this math. So just please remember when to add 30 degrees, when to subtract 30 degrees, when to multiply by square root 3, when to divide by square root 3. These four functions are everyday common in the power industry, and people get them backwards all the time. Three-phase power, just remember, it's 3 times A phase power, which is 3 times VAN IA cosine and the angle between the voltage and current for A phase. Reactive power, Q 3-phase equals 3 times Q of A phase. So 3-phase reactive power is 3 times reactive power of A phase, which is equal to 3 times VAN times IN, sine of the angle between the voltage and current. And then 3-phase apparent power is just 3 times the apparent power of A phase, or 3 times VA times IA. Technically, if I'm going to rewrite, this should be a, it's hard to draw here, but this should be VAN, if I could draw it like that. Okay, so 3 times VAN times IA. Okay, I would write the square root 3 one here, but okay, fine, let's do it. I mean, if that's what the textbooks show, I'll write it real quick. Give me 1 second. Let me get the drawing pad out. Okay. So let's go and put this here. That could be, no, that shouldn't be there because it's SA. Okay, this should also equal to square root 3 times V. So we had AN here, right? If I wrote VAN like this would be the line voltage, which would be VAB times IA. That's where, so the difference between here is that square root 3. Okay, that's if you're using a line be, which you probably will be, if I'm going to be all honest, because this is what the spec sheets will always give you. And I'm afraid you're going to not convert it back, and then you're going to 3 times voltage line, the answer is going to be wrong. So both of these exist. Just be careful which voltage you're going to use. That's the main thing. Okay, so that's all I have for today. So this pretty much concludes all of the power group, right? So you remember, you learned phasors, single phase power, right? SP and Q, power triangle, power factor, transformers, right? RLC circuits, power factor correction, 3-phase power, Y delta. There's a bunch of stuff we learned. I hope this is all the information you need. You should be ready to go to 141. You should be ready to get an internship in a power company, in all honesty, with this much information, and start really getting your hands into the power industry. Okay. So remember, there's going to be an exam coming up for this whole group in the next week or so. So please review everything, check everything out, and we'll be back for the next lecture topic. Will be a whole new section of circuits. So thank you for showing up. Thank you for learning power engineering, and you guys have a good day, and we'll catch you later.